Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is fluid conductors. Our objective is to examine general properties of fluid conductors, like pipes, tubes, and hoses in hydraulic systems. If we were to liken components of hydraulic system to organs in a human body, the pump would be equivalent to the heart, an actuator like cylinders and hydraulic motors would be equivalent to muscles. The passages leading to and from these components, hoses, tubes, and pipes, would therefore be equivalent to the circulatory system, the arteries and veins that supply muscles with oxygenated blood and remove waste. It is therefore worth a moment of our time to discuss these vital conduits that route pressurized flow from the pump to actuators and return flow back to the reservoir. Three general classes of conductors exist: pipes, tubes, and hoses. Pipes are inflexible, thick-walled steel conductors designed for semi-permanent stationary connections between static, non-moving points in a hydraulic system. Pipes cannot be bent and can ordinarily only make turns through the use of an additional fitting. Examples of fittings include 90-degree elbows, 45-degree elbows, T's, and reducer couplings, which make a transition from one pipe size to another. Pipes can be threaded or unthreaded. A threaded pipe for fluid power applications ordinarily make use of NPFT or straight threads. NPFT stands for National Pipe Taper Fuel, which are slightly tapered and depend upon slight deformation of the thread to provide a seal. For this reason, NPFT threads require assembly within a specified torque range to provide a proper seal. Repeated disassembly and reassembly, or over or under torquing a connection making use of NPFT threads, may over-deform the threads, leading to progressively increased leakage. Pipes with straight threads, in contrast, are not tapered and rely upon an additional O-ring to seal the connection. Unthreaded pipes, in contrast, obviously have no threads and are customarily welded to a flange, and the flange is then bolted to a subplate or manifold to provide a sturdy, leak-free, yet comparatively difficult to disassemble connection. Pipes are sized using two dimensions and a schedule specification. Outer diameter, commonly abbreviated OD, and inner diameter, commonly abbreviated ID, as their names imply, specify the outer and inner diameter of a pipe. Schedule refers to wall thickness, with Schedule 40 being standard and Schedule 80 being for higher pressure applications because of their thicker walls. Pipes are customarily sized using their nominal OD. The observant among you will note that the nominal, or in-name only, size of a pipe has absolutely nothing to do with the actual OD or ID of commercially available pipe. For example, a nominal Schedule 40 half-inch pipe has an OD of 0.84 and an ID of 0.622 inches. This corresponds to a wall thickness of approximately 0.109 inches, where wall thickness can be calculated as OD minus ID divided by 2. The division of 2 is necessary because there are two walls. Similarly, a nominal half-inch Schedule 80 pipe has an OD of 0.84 and an ID of 0.542 inches. This corresponds to a wall thickness of approximately 0.147 inches. You'll note the OD of the related nominal half-inch pipes is the same, and the ID is comparatively smaller for the higher schedule pipe. This correlates to a thicker wall, thus suitability for higher pressure applications. Do not think I am asking you to memorize this chart, nor am I asking you to accept this act of monumental nominal stupidity. Call me crazy, but a half-inch pipe should at least have one dimension that equals half-inch, but they don't, and you have to deal with it. In summary, pipes are strong but inflexible and cannot be bent. Any deviation in course with a pipe outside of a straight line necessitates the use of a fitting. Tubes, in contrast, are thinner-walled, semi-rigid metal conductors that themselves can be bent to perform minor bends or deviations in course without the use of an additional fitting. Tubes are also sized using OD and ID dimensions, with schedule being an indicator of wall thickness. Tubes, because of their thinner walls, aren't suited for extremely high-pressure applications, nor can they be threaded. Tubes, if they must be connected to flanges, pipes, hoses, or other tubes, ordinarily use flared, flareless or compression, or flat face or O-ring fittings to do so. A flared fitting uses a sleeve and a nut that grips the flared or expanded end of a tube. After sliding on a sleeve and nut combination, the tube is flared out to the proper angle using a flaring tool. When the body of an associated fitting is properly torqued to specification, the union provides a leak-proof assembly. A compression or flareless fitting, in contrast, does not require the tube to be flared to perform the seal. A ferrule, rather than a sleeve, kind of grips the outside of the tube by cutting into the outside surface when the fitting is assembled and properly torqued to specification.